our meeting of Warsaw Hadoop Ecosystem. Today the presentation will be given by our special guest, who is Kai Vogt. Kai is a senior Hadoop instructor who works for Cloudera and lives in Germany. So Kai will talk about Hadoop Ecosystem and also speak a few words about Cloudera, who is our sponsor of this meeting. So I think that we can start. We will enjoy the presentation.
Yeah, thanks Adam. Thanks everybody for joining in such a large number. And so I hope the kids that doesn't be too much in case of attention to what I'm having to say. Yeah, like Adam said, so I'm Kai. I'm working for Cloudera as an instructor, and I'm in town for training, which some of you are attending this week. So what we decided to do while we had a meetup this week at the same time, to have this kind of 1 hour event where I'm going to find out in a second who is already familiar with Hadoop, and then we will do a couple of components that you can find in Hadoop and why you use them. But before we start, like Adam said, so I want to drop a few words about Cloudera. That's the company that's paying for the PSA of easy right now. So Cloudera is a software company from California, and you might be familiar with Red Hat, who is a company in the Linux ecosystem. So they have a distribution, Red Hat Enterprise Linux. They sell services like support, training, management software. And we do the same thing in the Hadoop ecosystem. Yeah. So we have distribution, we have services, like the training we're running this week. So this is how Cloudera works. Again, basically a US company who just coming to Europe like mid or early last year. So we are growing. So if we're going to do something with Hadoop, you might see that company name again. And we're going to see a little bit what Cloudera has to offer for those who are interested in Hadoop. So before we move on, I want to have a quick hands up for everybody who knows what Hadoop is. So who has used Hadoop already somehow? Okay. So who has no idea what Hadoop is? Okay, cool. So what is Hadoop? Hadoop is an open source solution to solve big data problems. Yeah. So it turns out that very often data gets bigger and bigger, and it doesn't fit into a single computer. So Hadoop is going to be a distributed data platform. So you're not running Hadoop on a single computer, but you're going to buy multiple machines to build a cluster. So this is my cluster at home. It's kind of smallish, but it does the thing. And companies like Facebook and eBay and Amazon, so they're going to run Hadoop clusters with thousands of things. So they can't afford it. I don't want to mess up my apartment. But that's going to be the idea. We're going to utilize many computers to store petabytes of data. Yeah. So one reason, famous or popular example is the CERN in Switzerland. So the guys who claimed to have found the Higgs boson. And what they did to actually prove that the Higgs boson exists, which you can't really do with a microscope because you can't see it because it's so tiny. But what they do is they let particles collide. And they have detectors and sensors to see like the radiation effects of this collision, which they sample at a high sample rate, and there's millions of sensors. So that's a lot of data to be stored. They use Hadoop for that, and they use Hadoop to find out if the patterns they are seeing in that data set kind of prove that the Higgs boson most likely exists. So they store, for example, 80 or 90 petabytes of data a year. That's a lot. So if you think of the terabyte disk in buying nowadays, you take 90,000 of those, that's a lot of data. Okay, so what we're going to look at today is two things. The ecosystem, that's the components that we can use in the Hadoop infrastructure. And the second part is one component that we're going to look in more detail, for HBase. So what Hadoop has as its very, very most important or most inner part is a distributed file system. So think of a RAID system, mirrored and disk drive file system across all these nodes in your cluster. Yeah. So think of just concatenating all the disks to a large virtual disk and you get a distributed file system. And that's called HDFS, the Hadoop distributed file system. And it has some cool features, so it feels like a big FTP server to the user. So you just upload files, and in the background, the HDFS will take the content of the file and puts it across your nodes. And it stores it multiple times, so in case you are losing a node, we still can access all the data. Yeah. So think of a distributed, redundant file system that spans hundreds of thousands of nodes. So you can store petabytes of data, so you can have a real big disk. What I try to do is give always some little demo about all these components, and let's see if this works. So what I have here is, can everybody read the cover of the last one? Or should I raise the font size? Bigger. Does that work? Okay, I can barely see you, but hopefully then this thing. Okay, so what I have here is a tiny, tiny cluster. It's sitting in a virtual machine in my laptop. But let's just assume I'm having 50,000 nodes on the desk, and I'm going to access the file system. So what you get is the command line tool. There's a Java API, there's scripting APIs. You can mount the file system. But I'm just using this command line system. So I can create files, so it's really a file system, so that's nothing that's really surprising. Yeah, so I created a file system directory, and I can check my file system. Yeah. And this file system is in the cloud, in the cluster. I can upload files, so let's do that quickly. I should have some data. So it really feels like you're talking to a big FTP server with a disk of maybe up to a couple of petabytes. Yeah, so what I managed to do was create some files. So it feels like a Unix file system, and that's pretty much what it is in the background. Yeah, you can delete files. Whatever you expect from a file system, HDFS pretty much does that. With one exception, there's a big limitation in the file system. You cannot modify existing files. It's like a CD. So once you have written files to this file system, you can delete files, but you can modify them. So that's a limitation based on all the physics in the background and what the file system can do and whatnot. Think of it as a file system like your Unix file system. Okay, so back to our slides. So that's HDFS. So we can store our data on our hundreds or thousands of nodes. Now, very often, not very often, but eventually you want to process the data. So you want to apply some code. Maybe you want to scan through your distributed data set. And the idea behind Hadoop is when you want to process the data is there's not a single program that scans through the data, which means this program has to read all the data to be processed at one single spot. What Hadoop does instead is the code or the query that you want to apply to your data will be pushed to all of the nodes where the data is. Yeah? So we have a distributed processing layer. And that one is called MapReduce. Yeah? And MapReduce is a distributed programming framework which allows you to push code to the nodes where the data is. And that's why Hadoop is so scalable, because every node is going to work on the fraction of the data that is stored on that node independently to all of the other nodes. Yeah? So the rule of thumb is if you double the number of nodes in your cluster, you get twice the performance. So the execution time is half of it. You just had half of it. Okay, so this is the idea. So we have a distributed processing layer, and it follows a weird functional programming design pattern, which would take hours to explain. So just keep in mind, if you hear MapReduce, it's a distributed processing layer where the code gets pushed to the nodes where all the data is. So let's run some code. Again, there's a some kind of command line tool. The Hadoop tool will allow you to push the code to the nodes. You just have to tell in which jar file, which is a Java archive, the code is located that you want to run. You have to specify like the Java class that needs to be executed, and you specify the input directory, Shakespeare, and some output directory where the output should be stored. And then this cluster will get the code to all of the nodes. We run the query, the code in parallel. We get some kind of progress bar. And once the job is done, the output is in that output directory that I specified. If you eventually start looking at what this MapReduce API looks like, you're going to find out it's very simple. It's all wrapped around passing key value pairs around. So the API actually is very, very simple, but it turns out that you can really write complex algorithm in this simple API. So it's like a RISC processor, which only can do very limited number of operations, but you can build a lot of complicated things on top. Yeah. So my job is done, and I'm going to look at my output directory. And I see there's some files that contain the output. It doesn't really matter what this job did, but I guess you get the idea. So we process the data in parallel on multiple nodes, and the output actually will be stored by a distributed file system again. So this is these two components of Hadoop, the most important components. We have a distributed redundant file system, and we have a distributed redundant processing layer. So the processing layer is redundant because even if a node fails while it's processing the data, the cluster will resume this part of the job somewhere else because we know the same data is somewhere else as well. So this is HDFS and MapReduce, and they both come with Java APIs, which allow you to integrate the file system and to submit jobs, and monitor the file system and monitor the progress of jobs. And we have a wonderful developer training where we teach people how to program against this low-level API in Java. People who don't know Java hate this training. Well, they don't hate it, but they really have a hard time because Java itself is something complicated, and then learning the API is another story. So people who know Java, they love the API, but that's only a fraction of the people. So people actually would like to have tools to interact with these two layers other than Java. So in one command line tool we already have seen, that's this Hadoop FS file system shell, which allows you to browse the file system, upload, download files, create directories, rename files. So we have seen that. Fuse is short for file system and username. Those of you who know that will probably guess what it is doing. It's going to mount the Hadoop file system into your local Unix script. So you can operate with the Unix file browser on that regular file system. I don't have a demo for that because it's rather boring. Scoop is short for SQL to Hadoop, and that's what this tool is doing. It's connecting to a MySQL, Oracle, DB2 database, and it's transferring the content of one or more tables into HDFS. So I have a demo for that. Okay, so this is just a MySQL server with a bunch of tables. And I could look at those tables in MySQL. So we got a bunch of tables with a table name and the year the movie was published. And now you might want to use the MySQL server to process this data set. Yeah, you run a US query. But then if this little one processing the MySQL server, who has to read all the data and then calculate the output depending on your query. So we have one computer, a single thread on this one MySQL server, which runs the entire show. And if, for example, your data set is hundreds of, I don't know, gigabytes, even terabytes of data, this MySQL server is probably busy just half an hour to read all the data, because a single disk takes half an hour to read a gigabyte of data, a terabyte of data. So the idea is, let's load these large data sets into our HDFS and our distributed file system, and then use MapReduce to process the data in a distributed way. Yeah, because MySQL can't do that. Yeah, even an expensive Oracle server has limited support for parallel execution of queries. Okay, so I don't know why my cut and paste won't work, but what I just want to show you is the command line that I would be using. So what I try to do is to get access to the slides through Adam, and you will also get this demo script, so we'll repeat that if you want. Okay, so the idea simply is you can use Scoop to import a table from a MySQL server. All you have to do is you specify the username and password, which table you want to import, and then Scoop transfers the data from MySQL into HDFS. Yeah, and you can do that with one table, more tables in the database. So this is what Scoop does. Okay, so back to so this is Scoop. Yeah. And the demo would be to run these commands, and then we would see in HDFS we had the same content that we see in the table. Flume is a pretty new tool in that ecosystem. Imagine you have hundreds of web servers sitting in your data center, and they create log files. So every click that any user does results in a log file record in these web servers. And you might want to process the content of your log files. So you might want to find out what's the most popular web pages, what's the average duration of users on my website. Yeah, you want to use that to optimize and maximize your revenues for your advertising. So the idea is to have a tool that allows you to collect all these web server logs and put them in HDFS for future processing. Yeah. And that's what Flu is doing. Oops. Yeah, we learned that MapReduce has a very strong Java API. There's also an API that allows you to write all that code in a scripting language of your choice. Python, Perl, Ruby, PHP. So there's support for streaming the data to external scripts, and whatever the scripts return, go back into the MapReduce network. Yeah. So if you don't like Java, you can use the scripting language of your choice and get the same jobs done, but you kind of bypass Java. Yeah. And this is going to be the idea. So we have Java APIs for these two important layers, but we have tools that allow you to import the data from somewhere else and process them with something else for Java. Yeah. So this is going to be the idea. I'm going to have more of these things. There's Hive. Hive is a pretty cool tool. So if you know SQL, you're going to use Hive. Because Hive is a translator between SQL, which is this relational query language, and it translates this into the Java MapReduce job. So all you do as a developer is you write a human-readable SQL query. Yeah. So you specify where filters, you specify application, you specify group by partitioning, and Hive takes this and builds a very complicated Java MapReduce job for it, which gets executed in parallel on all my distributed data, and the output gets sent back to the client. Yeah. So that is actually very, very popular to import the data from somewhere, bypassing the Java API and the file system language, and then use SQL query to get reports out of the data. So you totally can join which actually was invented at Facebook. So Facebook is using Microsoft a lot. They don't know much Java, so they build a translating tool. The same thing happened at Yahoo, where people don't know much Java, but they are very good in scripting languages. So they created their own big data scripting language. And a translator that translates scripts in that language into, again, Java MapReduce jobs. And that tool is called Pig. And one more thing that fits in here nicely is the machine learning library called Hadoop. So, did anybody hear about machine learning? Okay, some of you. Those who have in my class. Okay, cool. So machine learning is something that is pretty new. There's different types of algorithms. Something that everybody knows is recommendation systems. So if you go to Amazon, Amazon knows which articles you looked at in the past. Amazon knows which articles everybody else is looking at in the past. Yeah. So they collect that. It's a lot of data. And what machine learning can do is learn through a machine which items are similar. Yeah, because the same people were looking at the same articles. Yeah, so if the system finds out people who were buying Beatles CDs also bought Rolling Stone CDs, in the future, when somebody looks at a Beatles CD, you get a recommendation of, hey, don't you want to buy a Rolling Stone CD as well? Because this is what we learned from the past. Yeah. So recommendation systems are the most popular machine learning example currently in existence. So everybody knows that from Amazon, eBay, Spotify, LastOrder, dating sites. So they all use machine learning libraries such as okay. And then there's HBase, which we're going to look at in part 2. Yeah, I hope you understand what HBase is. Okay, and I didn't have more space on the slide. There's going to be more of these ecosystem tools, and I just wanted to throw in some names. We are using Q, so we see a lot of weird names. And I'm not going to go into too much detail, but this just names that will show up in the new ecosystem. And there's going to be more. So whenever you go to vacation and you come back after 3 weeks, you see another tool showing up. And so we have like 50 tools on the library. So think of the ecosystem as of a Linux ecosystem. So you have the Unix kernel, the Linux kernel, which is responsible for storing files, which is responsible for scheduling processes. But that's not the system on a Linux box that you use. You want to have a graphical interface. You want to have the file browser. You want to have scripting languages. See the parallel? So Hadoop is such a distributed platform. So Hadoop has a distributed file system, distributed processing. So think of a Linux kernel that spans hundreds of thousands of nodes. And then we have tools like scripting languages, image export, file browsers. So think of Hadoop as the distributed Linux operating system. And this is what some people call it. It's the network operating system. And nobody is going to install Linux by installing the kernel and tools and graphical interfaces. People are installing distributions. So that's what Cloudera was thinking a couple of years back. Let's create a distribution that includes all these tools that we just have seen. So you don't have to install it manually, but you install things as one single package. And you find that on our webpage. It's all free. It comes with pretty good instructions, I guess. It comes as RPMs. It comes as virtual machines, so you can just install such a virtual machine, boot it up, and you have a one-node cluster up and running. It's exactly the same thing that I was doing. And it's all open source, so it's free. You have the source code. And you can do pretty much whatever you want with it. It's called CH, Cloudera's distribution including Hadoop, and we recently just released version number 4. So get it, it's pretty cool, and easy to use. Okay, so one part of the ecosystem is the patch HBase. So again, free open source tool. And what HBase tries to get you is the table structure on top of Hadoop. So think of the MySQL server, which has rows. Every row has columns, and in the fields we have different values. Or think of a big Excel spreadsheet, columns and rows. And now think of an Excel sheet that is petabytes big. So I don't know the limits of the Excel spreadsheet, but from my experience, after 100 megabytes, Excel becomes really, really slow. And MySQL, if you're going to have a table that is larger than 1 terabyte, MySQL becomes really slow. So what HBase is going to provide is an infinite size table. So you can store any data size. And we're going to utilize our nodes in the cluster, of course. So how does HBase do that? HBase simply cuts the big data set into slices. We call them regions. And every region is going to be put on one of my nodes in the cluster. And HBase will know where each slice is. So if you ask HBase for row number 290, HBase will take you to that node that hosts that region. So there's some kind of catalog, some kind of metadata inside HBase, which knows which row is where. Another cool thing that HBase provides is, if you don't have data for a cell, so a MySQL server and an Oracle server actually would need storage space to save that there's no field. So that's these null values in SQL. HBase actually doesn't need to store anything. So what HBase provides also is tables that are really, really wide, but you barely have data in the fields. So this is what HBase does. So we can store any amount of data by slicing things in these regions. What we also do is we cut the table vertically into column families. So we cut our table not only horizontally, but also vertically. So we can even store smaller slices on our Another cool feature of HBase, so let's look at such a single cell. Yeah? So a cell is identified by a row ID and a column name. And in that field, there might be a value. What HBase does is, it doesn't only store the value, it also stores the timestamp when. So that's something that a MySQL and Oracle server don't do. So whatever you put in that field, that's in the field. Whenever you're going to change that field, then the field has a new value. What HBase does is, whenever you change the field, we keep that old value in the background, and we just put the new value on top with the current timestamp. And so on. If we're going to delete a field, we actually don't delete that stack. We just put a delete marker on top with the current timestamp. And now HBase is a very cool API that allows you to go back in time, so you can do some kind of time traveling. You can ask HBase, what did the table look like yesterday at midnight? So it's like extended rollbacks. So even after you make changes, you can go back to your old data like days in the past. So that's really cool. So for those who want to know more details, actually what HBase is, it's a key value store. Where my key is the combination of a row identifier, which points to this row, the column name, which points in this direction, and the timestamp, which is like the third dimension. Yeah. So HBase actually is a three-dimensional key value space. Yeah. And in such a field, I store any type of data, numbers, strings, binary data. That's HBase. And the API is that simple. You only have a handful of API calls because it's a key value store. All you can do is access a single row, get to one. You can put something into the field. You can delete data, which actually doesn't delete, but just puts a delete marker on top of the data. Or you can scan the entire table or intervals of the table. And obviously you can create tables and drop tables and do stuff like that. But the API, the data access API, is really, really simple. So you might wonder, so who needs such a thing? So who needs to store petabytes of data in a table structure? I'm very sure everybody of you uses an application that uses this in the background. Whenever you send a message to somebody else on Facebook, that gets stored in such a big HBase table. Where the row ID is the user ID, but the column actually is where you are sending the data to, yeah? And the timestamp is just the history of your chat messages with that person. Yeah. So they use such a big table. And Facebook has 1 billion users. The user on average probably sends like dozens of messages a day. So that's really going to be petabytes of data. So what else? There is not just this Java API with the get and the puts and the scans. There's also Hive, which allows you to translate SQL into that table. So you can really work on this petabyte size table with the SQL query. There's other APIs, so if you know what Thrift and REST APIs are, you're glad to see that. This is what if you don't know what those are, you probably don't care at all. We have a Scoop connector, so remember Scoop was this tool that loads data from somewhere into MapReduce and into HDFS in the file system. It can also import into HBase. So it's well integrated into the entire ecosystem. And that's the end of my talk. So I didn't look at the time, it was probably half an hour, a bit more. So what I would like to recommend to everybody who is interested in big data, and you don't really have to think about petabytes. So if you have data sets that are tens or hundreds of gigabytes and you want to do something with it, like text analytics, scientific applications, Hadoop might do something for you. So you load the data into a cluster, and it's really easy to set up a 5-node cluster with hardware you have flying around using our distribution. There's people in this room that are familiar with Hadoop. You might find people in your neighborhood who can assist in setting things up. And yeah, just get going. Go to our webpage. There's tutorials, there's blogs. On Amazon, you can find the books on Hadoop. So who thinks that he or she is going to do something in the future? That's cool. Yeah. If you have some cool results, or if you're totally stuck, so Kai and Caldera, I forgot to make it on that. That's my email address. So tell me about cool things you're doing, because very often people do stuff that you wouldn't expect that people are doing. So they do image processing, or they do facial recognition with that. So I've seen a couple of cool things that people apply to YouTube. So if you have something cool to share, do it on Facebook or Twitter. So I'm monitoring a couple of videos, so you might see that. Yeah, other than that, we have plenty of time for questions. There's still some pizza and some Coke. So questions?
Actually, I'm wondering, it seems to be that HBase is used mostly in this kind of OLTP fashion. Am I right? It's more analytics.
Good question. So let's bring up this thing. It turns out that MapReduce is optimized towards throughput. So you can scan a lot of data sets in a short amount of time. So when you have to process gigabytes or terabytes of data, you probably want to do something with MapReduce, and one of the later problems. If you have this kind of transactional access pattern, so I want to have this record, this record, this record, then you want to go for HBase. So think of MapReduce being a big truck where you put a lot of stuff in it and then you take it somewhere for hours. Where HBase is like the taxi, the race car, where you just put a few things in it, but you just want to go short.
Okay, so it's so simple that it's so simple to use.
Yeah, it is. So HBase really is, you set up a table, and then you put any rows and any columns into it, and you have this very simple game of data. I don't know how to do that. So HBase has a Java API, also has an ugly command line tool, so HBase shell. So there are more questions because of this basically.
Can we use HBase to get into type? So let's say I have a database and I put data, there is a wide stream of data flowing all the time, right? And then I would like to do some aggregations on this data.
Yes. So Hive can run SQL queries, which gets translated into the MapReduce job, which can read the HBase data file. So that's like a 3-hop connection, but yes, it can do that.
Okay, and then the best interface to pump this data to HBase through Hadoop factory. So through HBase, or can I use some? It doesn't matter actually, right? Which interface I use to pump data.
No, you can use Hive, you can use MapReduce, you can use Scoop or Flume, so they all can create HBase data sets.
Scripting language, for example, JSON or something like this, JavaScript something do queries on something like Hive, but for JavaScript, for example.
So HBase has a Thrift API, so you can generate code stubs for pretty much any language. It has a REST API, so you can send URL queries.
Yeah, but I don't know my data model. Or let's say I need to assume that it will be pretty, it needs to be pretty flexible, right? So I don't know the names of the columns, let's say right now. I don't know how many columns I would have. So, and with SQL it's pretty difficult, right? So because the data looks like a structured data. I cannot assume.
Yeah, actually what you have to do, if you want to use Hive and SQL, you have to kind of layer the table view on top of the ATL data. Yeah. Oops, that's an option. Yeah, so a quick demo of how the API works. So you create a table, and the table has a name. You at least have one of these column partitions, column families. Okay, something running. More questions on Hadoop or HBase? Okay, I'm giving up that. I don't know what's wrong with my virtual machine. But the API is really simple. So you create a table, and then you do these could, get, scan commands, and you get the data there.
Integration via Scoop is online integration, or we execute C or of the database?
Well, Scoop is supposed to be run in intervals, so you always do incremental updates.
So initial import, and then from time to time, incremental, yeah, can just more data.
Actually, I have two questions. One is a infrastructure question. Given the ideas of virtual backups, there's a design, the instruction for something like that, we need to check how to do logical backups.
Okay, the question is how to do backups of a petabyte file system. Well, you need another petabyte file system, which usually is another Hadoop cluster. And there's Hadoop tools that allow you to replicate from one Hadoop cluster.
But I'm not talking about this speed. This is physical backup, logical. To protect from the removal.
Well, this simply is a logical backup because I'm not copying the physical blocks, so I'm not dumping the file system. So it's really a file copy.
Yeah, right.
It's more like
code and those data. The user can use the data. So I'm not protecting them from the physical data.
No, if a file gets deleted, there's some trash can feature. So if the user deletes a file, it goes into a trash directory, and then you can specify after what time the data physically is.
That's the only way.
That's the only way. There's no like file system snapshots, things like that. We don't have that yet. Hadoop doesn't.
There are some functionalities like that when you purchase the physical files, like from PC, there's a snapshot functionality.
Yeah, but the snapshot on a distributed file system is a not so trivial thing, and Hadoop doesn't have that yet.
Absolutely, it's not on the hardware.
Yeah, and Hadoop runs on, well, commodity hardware, so it's running on these normal servers. So there's no hardware support for functions.
Okay, so the next question about the Scoop, does it support that incremental?
Yes. So Scoop, you can tell Scoop just load the last 24 hours of data. You can apply filters, so Scoop can do that. We need to say again? I think it's really effective with multi-threading process, etc. Yeah, so Scoop actually doesn't read the data into one program and then upload it into the HBase. Actually what Scoop does, it launches a multi-job or multi-task job in the cluster, which then parallel
I have a question. We are doing
mostly text analysis of a range of documents, some machine learning and stuff. So we are not so much interested in instantaneous analysis of data which comes from a string. We have this data which is kind of static to a certain extent, and we are doing some analysis in the background, right? So which tools are best suitable for this type of job? So Iris is not a great example here, right? Flume is mostly for data which comes, dynamically changes, right? Yes. But which of these tools would you recommend for batch processing in the background? Yeah, so the tools on the right. So Flume is more like an online real-time importer of streaming log files, because log files get written constantly. So Flume is used to import that from directly into HFS. HBase also is a real-time online thing where you can perform changes. Pretty much everything else on the left-hand side is for doing things in larger intervals. So I use Scoop once at night to import the last 24 hours of data. I use Hadoop Ecosystem to copy upload files. And then I use one of these MapReduce systems to run batch reports to get aggregates or filter the data.
If you have, for example, a large number of small files, it's better to, it is reasonable to put them in HBase or just to concatenate archive somehow and then put to MapReduce. Assuming that you don't have a lot of access to HBase. But maybe sometimes your data will change, maybe you will analyze your files and then discover some information and you would like to start new files.
Yeah. So when you're storing the data, it does make a difference which component you're using, because finally everything ends up in HFS. So you usually base your decision on your access pattern in the future. Either to look up little tiny records, then you probably want to do some HBase model. If you really want to do like big reports and process a lot of data, then you probably want to use one of the MapReduce layers.
And if you process the data that is stored in HBase, but you process the data using MapReduce, is it much more slower or is it slightly slower?
Yeah, one good thing about data that you put into HFS through the HBase API, so you put all these different records, it's faster to then process them through MapReduce, because then I can batch process them. But if I want to have like single record access, I will go back to HBase. And the cool thing is, I only have to store the data twice. So in other related big data tools, you always have to transfer data from the batch processing side and that storage to the low latency online tool and that storage. And here we have one storage component, and we have different access patterns.
I have a question about HBase and responsiveness, because as far as I know, the whole system was designed with latency, but I could. So what can you expect for HBase? In my case, I've got really strong requirements for latency. Can you expect something like 99 queries, single queries, will end up in 3 milliseconds or something like that, or should? So can we expect something like that?
So, but again, so HBase is wrapped around primary key lookup. So you always have to put the row ID into the query. So get me that row, change the row, delete the row, and that is done in the range of milliseconds.
Okay.
Per node. Yeah. So if you have 100 of nodes, you can get like 1,000 operations per node. If you have 100 nodes, you can do 100,000 operations per second.
Does it make any sense to use HDFS for ordinary file storage?
Absolutely, yeah. So if you just want to store files, and we have some customers who want to store data, they don't really know how to process them yet because they just want to store it because it's so cheap to hold a data. So people just use HDFS as an archive.
Yeah, but even if there's a client which has 100 really small and tiny files.
Yeah, HDFS doesn't like that because there's an overhead for every file you're going to store. And HBase, HDFS prefers to have few large files because then you have just small overhead compared to all these tiny files, which for each file we have to store that information. Yeah. And HDFS supports file containers where you can put tiny files into large files. I think that's a tar archive, tarboard.
But do I have to do it, let's say, manually, or is it done by HDFS automatically?
There's command tools that do that for you. So think of a tarboard. So you take a subdirectory of files, and then you can create this archive.
When we have our Hadoop cluster, and what happens when one of the nodes goes down?
Yeah, Hadoop is fault tolerant, so any node that stores data can fail because the data is stored somewhere else. So think of a RAID system with disk. So if a single disk fails, the data is also somewhere else. Hadoop has some more other cool features on top of that. So if a node fails, data will get redistributed again. So we actually could lose another node with that data in an hour again, and then the data will be redistributed once more. So we're always trying to keep enough copies of the data. And also if we are processing data and the processing node fails, we just rerun that little part of the query.
What happens if name node fails? Other something like secondary name node or something else to make it fail.
Yes, so Hadoop has one single point of failure. It's called the name node, which was early enough time to explain all that, but since you're asking, so the name node manages the metadata of the file system. So the name node knows where the files and the content of the files are in the cluster, so on which nodes. And if that node fails, you need to have a standby node that takes over. And until like half a year ago, that took half an hour to bring back your file system. Now with the latest release, there's a high availability neighborhood architecture, so you can do that in like a couple of seconds. So there's some solution for that.
Is it master solution, or just one of these name nodes is active and the second is innocent?
Exactly. Yes.
So we cannot read from two.
Actually, there's another concept which is called the federated name node. So you can partition your namespace. So one name node is responsible for this part of the file system, and the other name node is responsible for that. And each of them you can set up as an active passive name node. But that's when you not create this direction.
Okay, I have one more question about the scenario which we are playing in the near future. So we are playing complex workflows of data analysis, in which a number of about five partner institutions will participate, and most of this will be on top of HDFS, and it will be based on data will be stored in HDFS and use MapReduce task, perhaps scripted in Python or Pig to process. But some of the partners would prefer to take the data out of HDFS and do this in a completely different fashion without using MapReduce paradigm and so on. And so what is the best kind of bridge that allows you to export? I understand that HBase is quite a good example. Well, we could in one of the workflows you can put data into HBase and then put a Thrift API or RESTful API, and that's the way to take the data out, process it in a completely different fashion, and then put it back in. So what other solutions apart from HBase would you recommend?
Okay, so if you want to pick little tiny records to be processed somewhere else, then you're right, HBase is going to be the thing. If you want to export large chunks of the data, you probably want to just do a file system copy using the mounting solution or this file system shell. Or use Scoop to load it into an Oracle MySQL server. From there on, the other guys are making further queries. Okay. So we have some import-export structure on the importing side.
Could you say more about WHUG here?
Yeah, WHUG is something like a cron system for Hadoop. So if you have jobs that you want to periodically run at 2 o'clock in the morning, you can tell WHUG to run this MapReduce job, to run this Hive query, to run this scoop import. You can even tell WHUG to run more complex things. So at 2 o'clock in the morning, run scoop to import some data set, then run Hive on top of that new data. The output should go back in HFS, and then you scoop one more time and export the data from HFS into MySQL. And then WHUG will do that whenever you want it to. So WHUG is like a cron for MapReduce or for Hadoop, which also supports some flows of multiple jobs executed after nodes. Hue is a web-based desktop application where you can use a web-based file browser to browse files and upload files and download files and view files. It contains a graphical SQL editor, so you can run Hive queries with a graphical tool. So it's just a desktop front end for some of these ecosystem tools. Where is pretty cool if you want to run a cluster on Amazon. Yeah, Amazon, you can not only buy processes, you can rent computers for an hour, a day, a week, permanently. So for example, you want to run a Hadoop cluster on 20 nodes, but you don't have 20 machines, you don't have data center. So what a lot of people do is they rent 20 PCs at Amazon's data center, and you would like to install all of that on 20 machines, which is looking like a very hard task to do, because you have to install 20 machines with the software, you have to configure things. And where does that for you in 2 command lines? So where requires a configuration file where you set up, I want to have 20 nodes on Amazon, here's my username, here's my password for Amazon, and then you hit enter, and where connects to Amazon, rents those 20 machines for you on your account, and your credit card that you also use for buying books, that will be charged for the time of those machines. Yeah. And it's not so expensive, it's like €1 or €2 for one machine per hour. So depending on how long and how many machines you're going to get, you might want to try that. So this is what it does.
It's based on chef or butter or
It's something else. So that's these 3 tools that don't really fit into that MapReduce or HFS picture, but still they are part of the ecosystem.
So the question was on HBase. If you have 2 data centers, is it possible to set up 2 clusters which replicate data online when master solution?
No. So Hadoop, in general, so all of these components, they expect the cluster to be in one geographical location. Because we really need latency and synchronization, so whoever is going to sell you a synchronized storage across long distance was missing the physics class where they explained light speed and speed of light. So Hadoop really wants to have a cluster in one location. What you can do is you can asynchronously replicate one way from one cluster to another.
And if you do so, it's easy to switch in case of failure of whole data the other one, and then you fix the first one, you switch back and still preserve the data consistency.
Yeah, but typically your applications are on that data center as well. So you can do that in MyCandy, you might miss some data. But that's something you would have to do manually, so there's no application for you
With the same time.
Is it the possibility of making more processing power to one job and less?
Yes. So the MapReduce framework has an interface for scheduling jobs. So you can assign more resources to certain users. So for example, the production users, the production jobs, they should get always 80% of the cluster resources, while jobs that I want to test get less resources. So you can kind of do this old type of mainframe scheduling.
One more thing, when you have a bit more complex workflows and you program using MapReduce, then you tend to have like dozens of temporary directories, right? That are, and sometimes you for one MapReduce job, you for example merge contents of you take an input contents from these two, then from the other three, and so on. So it's easy to get lost in this like maze of dependencies between the directories and which is for what is the schema of the key value pairs and so on. So is there a kind of, I don't know, a notation? I understand that to a certain extent WHUG could help here, but I'm not sure to what extent actually. Is there a standard way of describing the schema and the workflows and making it kind of easy? I'm looking for something along the lines of, I don't know, perhaps a UML kind of notation and then some kind of.
Okay, so one answer to your question. So WHUG indeed is able to run a flow of multiple jobs that need to be executed after the other. And WHUG automatically can delete all the temporary data that was created between two jobs. So WHUG can do that. The other question was how can I kind of manage this huge file system? So what are the meanings of the files I'm going to put? It's pretty much the same challenge to keep your Unix home directory kind of organized and clean. And we have seen a lot of customers where a lot of time went into laying out the file system. So this is the directory where the raw data comes in. We organize that by quarters or by days. This is the directory where the clean data goes in. So they really put a lot of effort into describing their file system structure and the flow of the data. So we use group to put data into the raw structure. Then we use pick to clean the data. Then we use hive to build reports. The reports get expired with those scripts every month. So that's something you usually have to do yourself.
Do you have some best practices or some video tutorial on that, or some experiences from clients, something like that? I mean, it would be very interesting to see in practice how this is organized.
So like I was saying, so if you have a more complex flow like cleaning data, pre-batching data, and so on, it's really a manual task. So I've seen a couple of customers where they created hundreds of pages, where which data goes and what's the meaning of which data set, what's the format of the data, because it's just a file system, so you can't see if a data set is a CSV file or whatever. There's another solution or ecosystem tool that might help you. It's called HCatalog. HCatalog, like the Hadoop catalog. It's like an inventory description of your files in HDFS. So you could say, okay, these files are representing my web logs. They have this structure as a time field, that's a whatever URL field. And I will make use of those fields as well. And you have a repository of the file structure. So that's something that is Cassandra is another key value store which kind of works like HBase. So another of these NoSQL stores or key value stores. It pretty much has the same characteristics as HBase. So it's a key value store distributed, wrapped around access on the primary key on the row ID. But it has its own storage layer. And that's why I like HBase, because it's using HDFS like all the other tools. And very often we have use cases where the data that we are storing we need to access in a batch processing way with MapReduce, or in a low latency random access pattern with HBase. And I don't have to transfer the data. If I would use Cassandra instead of HBase, I would have to transfer the data back and forth.
But you can connect Cassandra to the
Yeah, but they have a different format and
No, you can't.
So I'm not too familiar with Cassandra, but here in HBase or in Hadoop, everything is kind of on the same layer. I can connect Hive actually to HBase with the latest release. So everything is kind of working. I can use Screw and Flume to load data to HBase. And I don't think that you can do all that with Cassandra. But you're right, so there's different other tools that solve similar or the same problems. But what I like about HBase or Hadoop in general is so you get a single distribution which contains everything's working together. And I think with Cassandra you just have more administrative tasks. Yeah. So I'm not saying that Cassandra is the best piece of software. I just think that this whole integrated package makes more sense to me. So, since there's no more questions, I'm going to jump to the last slide, which says thank you, and I say thank you. So, I hope there was something new for everybody, and maybe you have some ideas on what to use Hadoop for. And if you have some cool success stories, please let me know. So, probably we're going to put the slide somewhere. So you're going to have access to that. There's going to be a video obviously, so you can share that as well. And yeah, so thanks again, and see you around.